So what is a three-phase circuit? As you know, the power is generated at a power plant. When a coil is rotated in the magnetic field set up by two magnets, and when the flux is cut because of the variable flux, the voltage is developed. And this voltage is in the form of sinusoidal wave. Now, why just use one coil? We can use many connections to the coil and increase the power that we want to deliver. So, we can use as many circuits or as many coils to rotate between the magnetic flux field. But this sinusoidal wave that we are generating, when we want to model it mathematically, this becomes a complex quantity. And as we increase the phases or as we increase the connections to the coil, the complexity also increases. So three phase is nothing but a optimized trade-off between the increment in the number of phases and a reduction in the complexity. Now we will see how three-phase circuit is actually used in what form. So a three-phase circuit is mainly used as a star or a delta connection. Now, what are star and delta connections? And what are the voltages and currents related in star and delta connections that we want to see? The diagrams that you see in the upper half of the slide here are nothing but the star connection. So, star connection is nothing but which looks like a star like this, alright, and the loads are connected in each branch of the star like you see here. The point at which all the three branches of the star connection meet is called a neutral point. And this neutral is connected to another wire which is carrying zero voltage. So basically, the current passes from this R voltage to the neutral voltage. And in each branch, this is reciprocated. So the branch which connects the load between 2 points, that branch is called as a phase, right? And the voltage between or the voltage across the load is known as a phase voltage, whereas the current carried by the load is known as phase current. There is another term which is known as line voltage and a line current. What is a line voltage? Line voltage is the voltage between two lines of a three phase. So this is nothing but V N, which is the voltage between two lines R and Y. Similarly, you have line voltage from Y to B, which is VYB, and another voltage from R to B, which is VBR. The phase voltage and line voltage may be different depending upon the type of connection, such as star or delta. So in a star and a delta connection, you have VPH from or the phase voltage VPH is equal to VRN, where N is nothing but a neutral point. Alright, and the line voltage is VRY. Alright, so this is how you can model a star connection and define the voltages and currents. The line current is the current passing through the line. Alright, here the current passing through the line and the current passing through the load are same, and hence the line current and phase current are equal. If you simplify this circuit here, you can see the circuit in the middle. This is how the circuit can be modeled, and as we can see, the vector diagram for the voltages in star connection is drawn alongside. You can see VNR, VNY and VNB separated by 120 degrees each. All these line voltages have equal magnitudes but are separated by 120 degrees in time and space. We can see this in this blue box. VR is given as with magnitude V and no phase difference with itself. Vy is having magnitude V but a minus 120 degrees of phase difference with the original V. Vb is having magnitude V and plus 120 degrees of phase difference. This plus 120 degrees phase difference can also be written as minus 240 degrees of phase difference. So basically, the time and space rotation of these phase voltages is reflected when we are writing the mathematical equations. Now let us see what is a delta connection. Delta connection looks like a delta, and each branch consists of a load. Now, from the basic definition that the current flowing across the load is known as phase current. The voltage across the load is known as phase voltage. Here we can see the currents passing through the load are the combinations of different line currents. Also, the line voltages is equal to the phase voltage. So, which was not in the case of star connection. As you can see, star connection had extra wire which is called neutral wire. The delta connection does not have such a neutral wire. You can simplify the delta circuit and see the middle diagram here. You will find the line voltages to be equal to phase voltages, and the phase currents are the combination of line currents. Mostly while we solve problems, the balance load is considered. What is a balance load? Three-phase circuit having all the loads equal is known as a balance load. Now you can see the RBY diagram in the right side again. So this diagram is again the combination of currents. We can write IBR over here, and we can write IRY and IYB. So if you expand these arrows like these, this arrow goes here and this arrow here. Again you see these arrows are separated by 120. Also, because of this IBR is in the direction of VBR, you can also write the voltages are separated by 120. So be it a star connection or be it a delta connection, the voltages and currents will be separated by 120 degrees in space and time. Now we have already summarized the voltage values for star connection. Let us summarize the voltage values for delta connection. In delta connection, as we saw, the voltage between the two ends of the load is nothing but a phase voltage, and this phase voltage is nothing but V in magnitude, 0 degrees phase difference with itself. Next voltage VBR will be same magnitude V and plus 120 degrees phase difference. VYB will be with minus 120 degrees of phase difference with the same magnitude. Now let us solve one problem to understand how to apply the concepts of phase and line voltages and currents. Let us see. So this is a problem number 1.20. We have to find the line currents in the given circuit. Alright, you can see a delta connected load here. Every load is equal 6 ohm plus J8 ohm. Now we need to find out the line current. That means we need to find out IR, IY and IB. Now we know from nodal analysis, if we put nodal analysis into the picture over here, we can find IR is equal to IRY minus of IBR. So that's what we have written here. And all these currents are taken as vectors because they also have direction. Now we have to find out IRY and IBR. In an instance, you can find out the IRY currents and IBR currents are nothing but phase currents because these currents are passing through a load. Now what is the phase current? Phase current is nothing but the phase voltage divided by the phase load. In delta connection, you know that the phase voltage VPH or VRY or say is equal to VBR is equal to the line voltages or the difference between line voltages, and the line voltages are given as V sub angle V minus 120 angle V plus 120 degree angle. Alright, the magnitude of all these voltages is equal. So we will take any phase voltage, say 100, because the voltage is given as 100. We'll write 100 and angle 0 and divided by the load 6 plus 8j. If you solve this, you get IPH is equal to this 10 is the magnitude and minus 53 degrees of angle. Now the interesting part to see is IRY and IBR are the phase currents. Because the magnitudes of voltages across the load and the loads are equal, all the phase currents will be equal. Alright. While solving this nodal analysis, we take IRY and IBR as is equal to IPH. Because these are vectors, we can solve these by the vector formula of subtraction and addition. We have IRY plus minus of IBR. So you can see this vector diagram here. IRY is oriented in this direction. IBR is oriented in this direction. But we want minus of IBR. Minus of IBR. So we'll be taking this direction. The angle between minus IBR and IRY is 60 degrees, and we are adding these two vectors. So we'll use magnitude of IPH square, which is equal to IRY. IBR is also equal to IPH, so magnitude of IPH square again, plus 2 into IPH into IPH. So that becomes 2 into IPH square and cos of 60 degrees. Cos 60 is nothing but 1 by 2, which gives us IPH into root 3. And this is nothing but IR, which is nothing but a line current. So we have the IPH. We need the magnitude of IPH over here, and we'll multiply it by root 3 to get the line current. So if you do this, you get IL or line current is equal to 10 into root 3, which is nothing but 17.32 amperes in magnitude. Alright. So this is how you can solve problems related to phase circuits. I hope you have understood. I'll meet you again whenever you call me. Thank you.